In this video, you're going to find the electric field resulting from a uniform infinite line of charge. Let's start by drawing a diagram. Here we have the infinite line of charge. I've drawn it along the z-axis. Rho L is the charge density given in coulombs per meter. The approach to solving this problem is to use Coulomb's law. The difference to what we've been doing earlier is that we've had, up to this point, just discrete point charges really that we're just adding together to give an electric field at a given point of interest. Over here though we have a continuous uniform charge density along this line. So we can't just discretely add anything, we have to break up this line into infinitesimal portions or little bits of charge. So imagine me cutting this line into tiny bits, and we'll call that dq, and we'll use calculus really to just add up all of those bits and find the electric field at a certain point or various points. So the principle is still the same, except we're using calculus this time instead of actually adding up each part and doing a summation. Just as a refresher, here are the unit vectors in cylindrical coordinates. Why I'm showing this to you is that cylindrical coordinates make this question quite easy to solve because of the symmetry of the situation. So just as a refresher, we have our a hat rho coming out in all directions. So here and all of these places. I've just drawn it in this plane, just arbitrarily, to keep things simple in a diagram. The phi will go all around the cylinder, and we'll have an a hat z positive in this direction, going up. Here you can see the advantage of symmetry quite clearly because you have this line of uniform charge density along the z-axis, and it's dead center of this cylinder. Let's apply Coulomb's law. We know that the electric field for a point charge is given by this equation, and as I've mentioned before, because we have a continuous line of charge with rho L as the charge density, we need to find a dq, or we break up that line into infinitesimal or very small portions. That dq is given by this, rho L times dz prime. And I'll show you how I got this in the next slides. So I'm just going to draw a few points here just to keep things clear. So this is our line of infinite charge, and at this point I've drawn this point of interest as, the source point is 0, pi over 2, and z prime. And just to be clear on what that is, this is the convention of notation I'm using. The rho phi z. So that would be my rho component, that's my phi, and that is my z component. Here I've written z prime as the convention that we use in textbooks and courses. The prime is just signifies that that is the source point. So whenever we have sources, we use a prime notation. And why we have pi over 2 over here as the phi bit is because I'm using x as my reference point. So x is my 0 angle reference point. If I move if I move in this positive direction this way, going from this x-axis to the y-axis would be 90 degrees, and so my pi over 2, so I have pi over 2 going this way from the x-axis to the y-axis. That's why I have pi over 2 over here. Remember that phi goes all the way around. And it's 0 on the rho because I haven't come out in any direction. I've just stayed on the z-axis. Now over here, I've just taken a piece of this line, and I called it dq. And to find it, I've just multiplied the charge density by a little bit of this z prime. So if I'd just done rho L times z prime, that would be incorrect because I'm not getting a little bit of charge then. It's just charge for that given z prime. But what I'm interested in is this dq, or a little bit of charge. So I must multiply the charge density by a little bit of z prime. And just to be clear with the notations and units, I have coulombs per meter multiplied by meters, because rho L is in coulombs per meter, and dz prime would be in units of meters. These cancel, and I'm just left with coulombs. I've chosen a point of interest now, so that's where I'd want to see what the electric field is. It's arbitrary, but since I've been doing everything in the ZY plane up to this point, I figured it would be easier to stick in that zone. So everything I've been doing so far is in the ZY plane. So in cylindrical coordinates, I'd have a rho that would go all around here in terms of the distance. So this radius would be of distance rho, and of course the unit vector would be in the a hat rho direction going all the way outwards. And I've just chosen my rho distance at this point because it is the simplest in the ZY plane to follow. So the point would be rho over here, coming out like this. Pi over 2 for the same reason as before, because we have our phi at 0 on the x-axis, moving this way, positive, it's pi over 2, and 0 on the z-axis for obvious reasons, in that at this point I am at 0 on the z-axis. Just to avoid any clutter, I've removed that point that I'd written down over here, the rho pi over 2, 0, and I've drawn in my position vector, r. Here I have my differential electric field element. To avoid any confusion, just imagine that this was a point charge, just a simple point charge, no d's to worry about. If you wanted to find the electric field at this point, all you'd have to do is draw a straight line from the point charge to that point of interest, and you'd extend that line. You know, I'm assuming, of course, that it's a positive charge. So, given a little bit of charge, it's the same idea. And that's the beauty of solving the question this way, is I can't do it discretely, but I can break up this line into infinitesimal bits or very, very small charges. And the same idea holds true. So for this little bit of charge, I'd have a little bit of electric field over here. As you can see that this is on a diagonal, I'll have some electric field component going this way and some going down here this way. Let's put that in terms more formally. So we can see that there's a component going in the a hat rho direction. Remember that a hat rho goes out in all directions, and because we're working in the ZY plane, the only a hat rho direction that I'm interested in really is the one that goes this way. So I can just say, well, the component of E going in the rho direction is in over here, and we'll call that the E rho direction. There's also a component of E going in the negative a hat z direction, and we'll define that by this vector dEz. So then you can write the infinitesimal part of E as dE is equal to dE rho plus dEz. All of these are vectors, and this makes sense because you're adding this vector over here with this vector, and it gives you dE, and that makes sense with our diagram. Now let's actually go through the math and see how we solve this question. So we know for a point charge we have that E is equal to Q over 4 pi epsilon r squared. We've done this in previous videos. And for a differential element of E, well, we have a little bit of E is equal to a little bit of charge divided by this constant and r squared. And we found dq earlier. So with this diagram that I had drawn earlier, let's find what a hat r is and what r is. So we know that the r vector goes from this source to this destination point. So the source is 0 pi over 2z over here, and the destination is rho pi over 2, 0. So with the subtraction, rho pi over 2, 0 minus 0 pi over 2 z, we get rho a hat rho minus z prime in the a hat z direction. So this is what the r vector would have been, and the magnitude of that is simply rho squared plus z prime squared to the power of half. So we know that r is this over here, and a hat r is just the r vector over here divided by r, the magnitude. So now we have r, we have a hat r, and we have dq. If we plug all of these into our dE, well, we will get this value over here. This statement, rather. And we can see that, this looks kind of messy over here, but all that is really is just a vector sum. But with these infinitesimal bits of E in the rho and z direction. Notice that the z vector is actually going in the negative a hat z direction. So to actually find E, we will have to perform an integral. But to simplify that integral, I would like to use cylindrical coordinates. I've just redrawn this line image over here to show you, just to reinforce what that looks like with the symmetry. How I'm going to use this to analyze the system is that I will vary one of the components in cylindrical coordinates, so I might vary phi and keep the other two constant, so I'd keep rho and z constant, and see how the electric field behaves as a result. So in this instance, I'm varying phi, keeping rho and z constant. When I do this, I'm just moving around this infinite line of charge, and doing so, I can see that the electrical field has not changed when I move around this this infinite line of charge. If you're confused by what this might look like physically, think about yourself walking around a tree. At a fixed distance from a tree, if you walk all the way around the tree, you're still seeing the same tree, except just at different angles with respect to some reference. Well, here our reference is the x-axis, our rho is fixed and the z is fixed, and we're just moving around this infinite line of charge. Now, varying z, well, whether we're at negative 1 million on the z-axis, or a million on the z-axis, or even 0 on the z-axis, you're still there's still no change in the electric field, and that's because the components of the z and at either end of this axis will cancel out on each other. So going up or down the z-axis does not change the electrical field. However, when we change our position with respect to rho, well, something interesting happens. The further we move out, the weaker the electric field, and vice versa. So the closer you are to that infinite line of charge, the stronger the field is. So that makes sense intuitively. If you think about the point charge, well, the closer you are to the point charge, the stronger the field is, and the further out you are, the weaker the field is. Using the observations I had made earlier with cylindrical coordinates, I can see that I can simplify this statement into something much easier to work with. So I know that E does not change with Z. So I don't have to worry about this Z part of this differential piece, because when I integrate, that will just go to 0. Knowing that, I just have to work with this over here, the rho component. That has made the integration much simpler. I don't even have to bother with this Z bit. I can just do everything over a hat rho, and doing so will give me this as the final answer. But really, note that the hard part of the question was getting to this point, finding this dE bit. This is just something mechanical, rather, solving this integral. You can do it as an exercise, but most of the money in terms of understanding is at this point. So that's our final answer over here. E is equal to rho L over 2 pi epsilon rho, all going in the a hat rho direction. Thank you very much, and I'll see you in the next few videos.